right? So we can pull the rho out of the integral, and everything else is going to be in the huge parentheses. And everything else is the integral over partial omega, the boundary of the control volume of the normal times the velocity. So let's look at them one by one. Let's first look at the left boundary. On the left boundary, the normal is -1, 0, right? On the left boundary, okay, the normal that points outward towards the outside of the control volume is equal to -1 and 0. And of course, my velocity vector is equal to u and v. So the integral on the left side is going to be -1, 0 dot with u and v, right, ds. So that's on the left side of the control volume. And let's just make it a little bit simpler. So -1 dot uv is, of course, just the minus u, right, times ds. So that's my integral on the left. It essentially points out that, I'm sorry, I think I missed the sign in the mass conservation. There should be negative of the integral, right? So when you take the negative of a negative, we get positive, right? So what we are looking at here is the amount of mass that flows into the left-hand side of this control volume, right? So it's essentially, if you look at the streamline here, it is how much mass has flowed from the left boundary into the control volume at a unit amount of time. Okay, so that's what this term is. Correspondingly, if we look at the right, my n is equal to +1 and 0. Now with the +1 and 0, we get this n dot with v is just a u, right? And with the negative sign, we basically get minus integration on the right, u times ds. I mean, in this case, ds is basically dy, right? And this minus term is how much mass has flown out of this control volume. If you follow the streamlines on the right side of the control volume, that's how much mass has flown out. And of course, we also have two other terms on the bottom and on the top of the control volume. And if you just look at the unit normal pointing always out of the control volume, you're going to find out that on the bottom, I have integration on the, let's say, bottom, v times dx. On the top, I have minus, let's say, integration over the top of v dx. Now, the integration on the bottom is how much flow, how much mass has flown in from the bottom during a unit amount of time. And the minus sign of integration on the top is how much mass has flown out of the control volume per unit amount of time. All right, so this is the case of, this is basically writing the general conservation of mass in terms of this particular square. And then let's take the square and make it shrink it to 0, right? So let's shrink the square to 0, and several things happens. So as you shrink the square to smaller and smaller squares, this equation always satisfies, right? Because this equation is satisfied for any control volume I draw. So no matter how big or how small the control volume is, this is true. So we can shrink to very small values without any problems. So if we shrink this omega to a point, what happens is that, okay, my integration over the left side of the u times dy is basically, it's going to become what? It's going to become the, essentially my u is going to become more and more uniform over this smaller and smaller length, right? So basically what I have is u at the left side of this control volume times the length of this, the height of the control volume, basically times delta y. My integration on the right of u dy is going to become u on the right of the control volume times delta y, and essentially integration at the bottom of v times dx is going to become closer and closer to v at the bottom times delta x, and my integration on the top of v dx is going to become v at the top times dx. And now let's look at what the mass conservation is going to give us. So if you combine all of these, and the green equation, which is the conservation of mass, becomes, okay, u on the left minus u on the right times delta y plus v on the bottom minus v on the top times delta x. That, well, of course, times rho is equal to 0. But if rho is something non-zero, then this thing in the parentheses has to be equal to 0, right? And now let's take this equation and divide this equation by the area of the control volume. What is the area of the control volume? It's delta x times delta y. Okay, so if you divide the both terms by delta x times delta y, divide by delta x times delta y, what we get is u left minus u right divided by delta x plus v bottom minus v top divided by delta y is equal to 0. Okay, and again, we are taking this control volume to an infinitesimal square. So for an infinitesimal square, the left minus right of the velocity is basically divided by delta x is the derivative of velocity with respect to x, right? So this equation finally becomes, well, it's the negative of the x derivative. So this becomes partial u partial x plus partial v partial y equal to 0. Make sense? Any questions so far?